back at thread safety again. So thread safety is an issue that we talked about when we had that example with the counter plus plus and counter minus minus, and you made all the different interleavings and saw which ones worked and which ones didn't. And this is a general problem when we introduce concurrency to our programs. If we have multiple threads, or in general, multiple processes, potentially executing concurrently or interleaving in different ways, we have to think about thread safety. I encourage everybody, again, I'll keep saying this, take operating systems in the fall, and we study these issues in a lot more detail, not only thinking about when the situations occur, but be a little bit more careful about how, as programmers, we avoid those situations and take care of those situations. And we look under the hood to see what has to happen at the operating system level, and maybe if we're in Java, the Java virtual machine, to be able to ensure thread safety when we need it. All right. So basically what we want to do is be thinking about situations where some data, some shared data, might be used by two threads at the same time. And it only matters if one of those threads, or usually the most dangerous situation is if two threads are trying to modify it at the same time. But it can be that one is just looking at it and one is modifying it, that you end up with problems. So we saw that example with the counters, but let me show you another example here in the context of a linked list data structure. So I think just about all of you have seen this example code before, the simple linked list that we use in the data structures class typically here. And let's suppose that we have one of these linked lists, and it's an instance variable of a class, and we have two threads operating on that class. And each of those threads, starting with an empty list, like we see constructed here, calls the add method. And ideally, what would happen here is if two different threads call the add method, after both are done, both of those values are in. Whichever one adds last is the value that's going to be at the head of the list, because these simple linked lists, if you don't give it a position, it adds it at position 0, because that's the most efficient thing to do for singly linked lists. So anyway, in whatever order these two things execute, we would expect to see either a 1 and a 2 or a 2 and a 1 in the list. But if we think about this, if we think about the code that has to add this stuff, I pulled this out of my code from the data structures class. There's an if statement that looks like this. If the position is equal to 0, that means we're adding at the beginning of the list, and that's ultimately what's going to happen if we add without a position parameter. We add at the beginning of the list, we're going to replace the head of the list with a new node that contains the object I'm adding, so either the 1 or the 2, and its next reference will be the old head of the list. And this is great. You can draw some pictures of this. I'm sure you have drawn pictures of this. The first one that gets added, let's say the 1 gets added first. OBJ would be a reference to an integer 1, and head would be null. And then the new head of the list would be a reference to the node that had the 1 in it. And then we come along and the other thread tries to add the 2. At that point, head is the list that has, it's a reference to that first node. So the next reference of this new node will be the node that contains the 1. We're constructing a new node that contains the 2. So the head of the list now is the node that contains the 2. Any questions on that? I probably feel like I should have drawn a picture of that. But did you get the idea? Did you get the mental picture of what we're looking at here? All right. So now suppose that the add calls happen pretty much at the same time. So they both come in and see that position is 0. That's fine. They both come in and head is null, because there's nothing in the list yet. Then they both call the simple list node constructor, one of which constructs a node with a 1 in it, and its next reference is the old value of head, which is null. At about the same time, the other one comes in, constructs a new node with the 2 in it, and its next reference is null because head was null. So far, that's perfectly all reasonable stuff to do. So they've both done this part, but neither has yet done the assignment to head. So one of them continues, and it assigns the head of the list, this shared variable in the list, to be a reference to the node that contains a 1 and has a null next reference. Then the other one comes in and it assigns head to be the node that it just created, which is the one that has the 2 in it, which also has a null next reference. So what we ended up with is one or the other of those values in the list, even though we think we added 2 values, but we only added one of those values. This is another example of a race condition, and that's the same situation we were talking about with that counter plus plus and counter minus minus. Let me stop and see if everybody sees that issue at least. Can you raise your hand if you're following along with this, if this makes sense so far in Zoom? Or ask a question if you're not, that'd be even better. Okay, maybe this isn't so bad. Looks like we've got about 2/3 of the hands have come up and gone back down. So I'm assuming everybody else is just not raising their hand instead of not asking questions if they need it. All right, good. So assuming that's the case, we need to deal with this. This is a situation that can come up all the time. There are lots of data structures that you might use in an object that has multiple threads potentially modifying that data structure within that object. There are a number of solutions to this. In this particular case, we can fix it entirely if we use that synchronized keyword that we saw in the ATM bank examples. If we just stick synchronized in front of the add method, then we know that at most one thread can be executing the add method at a time. Java will take care of that for us if that synchronized keyword is there. That would work in this case, but it's in some ways a bit of overkill. In fact, sometimes when people are doing this, if you're concerned about thread safety, you just might make all of the methods of your entire object synchronized. And that means only one thread at a time can be executing not just an individual method, but any of the methods in the entire class. The problem with that is that it'll do what we'll call serialization. It's going to serialize all access to the methods that are synchronized, not just when there's a potential problem. So there's no problem if 3 or 4 different threads were all calling the get method of the list, or 3 or 4 methods are all iterating over it, or anything along those lines. Those are perfectly safe things to do, and we would like our threads to be able to do this concurrently if it's not going to be a problem. So the problem is that we'd be reducing our concurrency a little bit too much, more than necessary, and that's going to limit the efficiency of our programs. One of the motivations for using threads, we've been mostly using the motivation so far that it's convenient to write threaded programs in the context of things like animations. But soon after we get back from the break, we'll at least see 1 or 2 examples where we want to take advantage of our multiple processing cores. And if we put synchronized in too many places, all of a sudden we have a whole bunch of our threads sitting and waiting their turn to have access to a structure, when really they could be executing concurrently. So there are also computational costs associated with using the synchronized keyword. Every object in Java comes along with what's called an intrinsic lock. This is one of the key pieces for the day today. And that's a piece of data that's associated with every single object we create. You've created a whole lot of Java objects, never thought about the fact that every time you construct a Java object, it's got an intrinsic lock associated with it. And that is just in case there are any synchronized methods, that intrinsic lock will be set or locked so that that object cannot have any of its other synchronized methods executed at the same time by any other thread. And that locking and unlocking and checking to see if it's locked, all of that comes at a cost. So what we'd like to do is use this synchronized keyword, but do it such that we minimize the amount of things that are synchronized. The other problem with just placing the synchronized keyword all over the place is that this doesn't handle all the possible unfortunate thread interactions that can lead to race conditions. Sometimes it's, I call this method followed by that method followed by that method in one thread, and I call some method followed by some method followed by some method in another thread. And it's the ordering in which those methods are being called that could be a problem. And that's what we're going to look at in just a couple of minutes. Before we go on to that particular piece, I will mention a little bit about completely synchronized implementations of data structures. So I've alluded to this a few times this semester, that we've got the java.util.vector and we've got the java.util.ArrayList, which for most purposes behave identically. There are some minor behavioral differences. You can find web pages and things like that that describe it. But the most important difference between a vector and an array list is that if we were to look at the source code of the vector, every method is declared as synchronized, whereas array lists are not. And that's why we generally teach you array list rather than vector, because when you're doing all this single threaded programming for the first 2 2/3 programming classes that you have in Java, you're not creating other threads. So why pay the overhead of all those synchronized methods in the vector class? So we'd use the array list. If we're using array lists in the context of threads, we need to make sure we use them safely. The next piece here that I want to mention is that Java has a mechanism that can take any of its existing list implementations, notably of the array list, but there are others, like the linked list implementation, for example, and it can construct what we call a thread-safe version of that list where all the methods are synchronized. There is a static method in the class called collections, collections.synchronizedList. And what you do is you construct your array list or your linked list or whatever else as you normally would. Then you pass it to this synchronized list method, and that'll return to you another list, which is the synchronized version of it. And as long as you access your original list only through the reference that comes back from the synchronized list method, then you can be guaranteed that at most one method at a time in that list is going to be executed. And since this is a common thing in other data structures, the Java API also provides things like collection.synchronized collection, collections.synchronized map, collections.synchronized set for other things that you might want to use.